This topic is a review of the Fourier transform with an emphasis on two-dimensional discrete transforms. The reason we're studying this is that we want to represent images in the frequency domain or Fourier domain and understand the operation of filters in this domain. So what we'll be covering is the Fourier transform itself, definition and properties, then focusing on the two-dimensional discrete Fourier transform, then covering the convolution theorem, which says that multiplication in the frequency domain is equivalent to convolution in the spatial domain, and vice versa. And then later, with this preparation, look at filters and applications such as smoothing, sharpening, and enhancement. So recall that the Fourier transform or Fourier analysis was invented by Fourier. And the main idea is that any periodic function can be expressed as a sum of sines and cosines. This is called a Fourier series. So given enough terms, the function can be represented exactly. So this shows a sawtooth function. And what we show here is the first couple of terms of the Fourier series. So this is the first 5 sines and cosines, which added together do a pretty good job of approximating the original sawtooth function. If you have enough terms, of course, you can represent the function exactly. So we're going to use complex numbers to simplify the representation of a Fourier series. So recall that a complex number is a combination of a real and imaginary component, where j equal square root of minus 1 is the imaginary component. So we can think of it as a point on a two-dimensional plane. We've got the real axis, the imaginary axis, and this is our complex number represented by this point here. So in polar coordinates, this is a vector of length c and the angle theta with respect to the real axis. So you can write it in this form here. So the key thing is that Euler's formula says that cosine plus j sine theta is e to the j theta. So that allows us to go from the explicit sines and cosines to the exponentials. Just some other preparation. The complex conjugate is defined as the complex number with taking the negative sign of the imaginary part I. Matlab has functions to deal with complex numbers. This is of type complex. We can do a complex conjugate, an absolute value, or take the angle theta. So the Fourier series then, instead of writing in sines and cosines, we can write it as a sum of exponentials of this form here. Just some more preparation. The impulse function is helpful to understanding Fourier transforms. The impulse is defined as this delta function, which is 0 everywhere except at t equals 0 when it's infinity. But we constrain it such that the total area integral of that is equal to 1. So the shifting property says if we integrate any function multiplied by the impulse from minus infinity to infinity, we just pick out the 0 term because delta is 0 everywhere except for t equals 0. So we just get f of 0 as a result. Or if we write the delta function as t minus t0, this term is 0 everywhere except when t equals t0. So again, we just sift out or pick out the term of f where t equals t0. In the discrete domain, very similar. The delta function is defined all zeros except at the origin where it's equal to 1. And we also have the equivalent shifting property in the discrete domain. So the Fourier transform is defined as the integral of a function f of x from minus infinity to infinity of f of x times e to the minus j 2 pi ux. So this produces a value for a new function, capital F of u, at the value of u, whatever we pick. The inverse transform, we can recover the original function by integrating f of u, and very similar except we have a positive sign instead of a negative sign for the exponential. So we can think of x as being a spatial domain because we're working with images, and u is a frequency domain, like a spatial frequency. We often write a script f to mean the Fourier transform operation here. So if we apply the Fourier transform to small f of x, we get capital F of u. Or if we take the inverse transform to capital F, we get small f. So these two functions are called Fourier transform pairs. If you know one, you can recover the other. Here's an example. Let's find the Fourier transform of this simple function called a box or rectangle. So this function is 0 everywhere except between minus w over 2 and w over 2. So we plug that into the definition of the Fourier transform, which is easy to integrate. The exponential is just the exponential. Plugging in the limits, we get this difference of exponentials. And that we can recognize is an identity for sine of a quantity over the quantity, like that. So this function is well known, and it's called the sinc function. And we'll see it over and over. And it has this form here. So kind of a sinusoid, but with decaying lobes like that. If we take the absolute value, it looks like this. The discrete Fourier transform is very similar, except we use summations instead of integrals. So we're summing from x equals 0 to x equal m minus 1. So we have m total values of the original function, and that's also how many terms are in the values are in the transform function. Note there's a constant here of 1 over m in the inverse transform. So we can consider the function and this transform to be periodic. So if we have a function defined from 0 to m minus 1, we consider that as repeating infinitely in both directions. The special case of u equals 0, so capital F of 0, if we simply plug in u equals 0 here, this term becomes 1, so we're just summing over f of x over all values. So that's kind of a DC term, the total energy of that original function. Just a note on units, how spatial units relate to spatial frequency. So we can think of x as having length, say meters. Frequency has units of 1 over length. So if we have a function that we sample at these integer spacings, that actually represents a function sampled at these points, namely f of 0, f of delta x, f of 2 delta x, etc. Similarly, we have the transform, and that represents frequencies at 0 frequency, frequency of delta u, 2 delta u, and so forth. So the lowest frequency, of course, is 0. It's f of 0. That's the DC term. But the lowest non-zero frequency is this one, f of delta u. The highest frequency, of course, would be this highest term here. So the longest possible wavelength we could have is where we have a complete repeating curve like this, like a sine, that would fit entirely within our m samples. So that represents the frequency delta u. So the frequency is just 1 over the wavelength, which is 1 over m delta x. So that can relate units of spatial sampling to frequency sampling. Here's an example in Matlab of performing the 1D discrete Fourier transform, just directly using the definition on the previous page, applying that to some input series that we create f of 1 through f of m. So if you plug in, let's say, the rectangle function like this, note that I centered it around 0, so it actually straddles 0. Then the output transform is this series of complex numbers. Note that it's basically all the imaginary parts are 0. So that's a special property of this rectangle function. Actually, any the rectangle function. And if you plot these real values, you get what looks like a sink. And remember that it's periodic, so this piece is repeated over here. So centered around 0, it's a sink. So that transform is actually kind of expensive because it has 2 nested loops. So this is a faster way to do it. It's an algorithm called the fast Fourier transform. And I won't really cover it except that just to say it's the standard way of doing Fourier transform. It's based on the idea of dividing the problem into 2 recursively and computing the transform of each. So that reduces the cost from m squared, where m is the number of samples, to m log m. So quite a savings it can be. And Matlab has a function to do that called FFT for fast Fourier transform. Some important Fourier transform pairs. We've already seen the rectangle transforms to a sink. A cosine transforms to 2 impulses. A sine transforms to 2 impulses but in the imaginary domain. And a Gaussian transforms to a Gaussian. So this is symmetrical, so either of these can be the spatial function and the other can be the frequency, so you can go either way. An impulse transforms to a constant. You can see that just by plugging in the impulse into the Fourier transform definition, as well as a shifted impulse transforms into a complex number. Finally, we're going to see the use of, this is kind of handy, the function that's a series of impulses, or a comb function because it looks like a comb. It's a summation of impulses separated at delta x. So that transforms to a comb function at separated by intervals of 1 over delta x. So the wider this spacing gets, the narrower this spacing is. And just showing the proof here, I won't go into that.